In the last video, we looked at the Kalman filter, which was the method for performing filtering in a linear Gaussian state space model. And we developed a pair of steps which form a recursion, which take the filtering estimate at the previous time step, combine it with a new measurement, yt, and return the filtering distribution over the current time step. And what we're now going to do is dive down into the nitty-gritty using the model and the sum and the product rule in order to show that this procedure that we pulled out of a hat is in fact the correct procedure mathematically for doing this. And the way that we're going to do this is actually we're going to proceed backwards. We're going to show that this second step is correct, and then show that this first step is correct. So we're going to look at this one first and this one second. Good. Okay, so here's how we're going to approach that. Of course, everything here is just going to involve our modeling assumptions combined with the sum and the product rule. So to remind ourselves, the model comprises latent variables, which are x, and observed variables, which are the data. And here I have written down the joint probability of our latent variables and our data. We're going to need that a lot. This is the likelihood function in here, and this is the transition function that we've been used to looking at through the last few lectures. Good, so standard notation, and for reference here, I've put up the rules of probability that we're going to use, the product rule and the sum rule. Good, okay. So our goal is to sort of use these together to compute the filtering distribution. So let's write down our filtering distribution to start with. That was this magenta quantity that is the probability of xt given y1 to t. And we're going to do something kind of subtle. We're going to split off the conditioning here. So we're conditioning on y1 to t. We're going to split it off into all of the y's up to and including the t-1th data point and the new y that's newly arrived. And the reason why we're doing that is because we want to tease apart the contribution from the current y, yt, from all the y's that came before it, y1 to t-1. That was, you know, the flavor of the update that we saw on the previous slide. It took the current likelihood function and multiplied it by the information from all of the y's that came before that current time step. So that's why we're breaking apart here. And now we're going to go in and we're going to say, let's use the product rule here. So this rule up here to decompose this, to write this guy in a bit of a different way. And the way we're going to use the product rule, well, we can see that x of t here, it needs to be associated with a. So we'll make the correspondence of a and x of t. And here we can see why this breaking up trick is going to be useful. We're going to associate y of t with b and y of t minus 1 to t-1 with c. Okay, so we plug this into the product rule just to make sure that I've done that correctly. So b here, of course, is equal to yt, so we get a yt here. C is equal to yt-1, so we get y1 to t-1 here. In here, b is equal to y of t, so we get y of t here. A is equal to x of t, so we get x of t here. C is equal to y1 to t-1, and so on and so forth. Okay, so we're just substituting it in. We're not really thinking very hard, having sort of done the thinking in this sort of clever way that we're breaking apart y into two parts, y1 to t into two parts. Okay, so it's kind of looking like we've made a bit of progress. The reason why I've gone this route is because, this second term looks familiar. This is the forecast that we saw on the previous sort of cartoon description. It's our forecast of what x of t should look like given y1 to t-1. So this looks like the bit that was shown on the previous slide. This bit looks a bit different, okay? It's the probability of y of t, which we need, but here we've conditioned it both on x of t and y1 to t-1. But now we realize a really important fact, which is if we're interested in the value of y, let's yt, let's say y3 here, without loss of generality. If we know what the value of x3 is, then there's no extra information in all of these y's here. because they only affect y3 through x3. So in other words, this distribution here, p y of t given x of t and y1 to t minus 1, this is equal to just p of yt given x of t. Okay, another way to say this formally is that y of t is conditionally independent of y1 through to t minus 1 given x of t. And that's essentially what the structure in the model encodes for us. That's what the model states as a conditional independence assumption. So that means, as I said, we can rewrite this thing as just p of y of t given x of t. And you can see this now looks like the update we had before, whereby we take the likelihood from the current time point shown in red, that's p of x of t given x of t, p of y of t given x of t, and we multiply it by the forecast. Now, one benefit that comes from this more mathematical treatment is that the constant of proportionality here, so we said we had to normalize this and make sure that everything normalizes. If you compute the normalizing constant after you take this product, that normalizing product is p of yt given y1 to t minus 1. And this thing is going to be everything we need to do learning, it turns out, or everything we need to do to compute the log likelihood. And that we'll return to later, but in a nutshell, the log likelihood of the parameters. So let me write down the likelihood of the parameters here. Notice this is a different likelihood from the likelihood of x of t. There's two likelihoods focusing around here. For the inference problem that we're looking at in filtering, we're trying to estimate x of t, and each observation contributes a likelihood factor, p of y of t given x of t. There's another likelihood that we're interested in when we do parameter estimation, and that's just simply the log probability of y1 to t given theta, the probability of the whole sequence given theta. This is a likelihood of the parameters now, not of x of t, or actually a log likelihood as I've written it down here. And this thing can be written down as log of the product from t equals 1 to big T of p yt given y1 to t minus 1 and theta. Okay, so I've decomposed the likelihood as using the product rule essentially into a product of the next y of t in the sequence given all of the previous ones and the parameters. And you can see that this thing therefore involves producting up this constant of proportionality, which is coming from the filtering step. So there'll be more on this later, but essentially, if you keep those normalization constants around and then product them together or sum up the logs, then that gives you the log likelihood. You can write the log likelihood in this way. Good. Okay. So this is another reason why we're focusing on this filtering algorithm here, because it's intimately related to what you need for learning. Okay, enough about that aside. One thing I've yet to show you is the veracity of the first step. Okay, this first step in which we compute this probabilistic forecast. We've shown the second step is all hunky-dory and obeys the sum of the product rule and the modeling assumptions. Let's just dive in and make sure we're doing the forecasting step correctly. So let's take the forecasting distribution shown in blue here. And again, we're going to do one of these subtle tricks. So in this case here, we're going to introduce the variable xt minus 1 by using the sum rule. Okay, so we're just going to use the sum rule and say the probability of xt given y1 to t minus 1 is equal to the probability of xt and xt minus 1 given y1 to t minus 1, integrating out that variable xt minus 1. And you can see the exact correspondence to the sum rule here. Okay, so that's all well and good. Why have we introduced xt minus 1? Well, we know we want this update here for the probabilistic forecast to involve the old filtering distribution, and the old filtering distribution was the probability of xt minus 1 given y1 to t minus 1. So we need some xt minus 1s to be introduced into this equation. Good. And now we're going to use the product rule in a simple way, and we're going to break out x of t minus 1. We're going to write down the joint distribution over x of t, and x of t minus 1 is the probability of xt minus 1 times the probability of xt given xt minus 1. That's essentially what we're doing. And of course, we've got one eye on the prize here, and the prize was making sure that the old filtering distribution showed up here, and that determined which way round we were going to apply the product rule. Good. So this now starts to look very much like the equation we had on the cartoon description. This is in fact correct. This is the old filtering distribution. This second term is a bit different at the moment. It includes x of t given x of t minus 1, but there's this extra piece we're conditioning on here. And again, it's the conditional independence assumptions which tells us that this thing is not required. So again, if you want to know, say, the value of the latent variable x3, and you know the variable x2, then you don't, or no extra information is provided by the variables y1 and y2. Okay, this is due to the Markov assumption in the latent variables. The only thing which affects the variable x3 is the variable x2. So if you know its value, then that's all you need to determine the value of x3. So that means because of the conditional independence property specified by the model, we can essentially ignore this part of the conditioning here. This is equal to the probability of xt given x of t minus 1. And hey presto, this has recovered the first forecasting update of the Kalman filter. This is also called the prediction step of the Kalman filter, as well as the forecasting step, because you're predicting one step ahead. Great. Okay, so this is the formal derivation of the Kalman filtering recursions. We could have replaced all integrals with sums, and we would have got exactly the correct updates for the discrete hidden state HMM, and that's called the forward filtering algorithm. For historical reasons, again, it has a different name. It wasn't developed by Kalman, and it's called the forward filtering algorithm instead, but it plays exactly the same role as the Kalman filtering algorithm. Great. So in the next lecture, what we'll now go and do is actually figure out how would you implement this on a computer. At the moment, I'm showing things in terms of integrals and distributions. Let's dive down and actually put in the form of the linear Gaussian state space model. Actually, the updates here haven't committed to particular distributional forms over P of y of t given x of t or P of x of t given x of t minus 1. It's valid for any distributional form. So what we'll do is we'll go and substitute in Gaussian functional forms for those that we have in the linear Gaussian state space model. And that will lead to the algorithms that you'd actually implement on a computer.